Can people hear me online or? Okay. I think I muted myself sometime. All right. Thank you. Okay. So just a reminder about tomorrow's test on chapter 2. Okay. I think I had mentioned this in my announcement last week, but in case you don't read announcements, it's here again. Okay. Some of these problems are a bit lengthy by nature. Okay, I don't have to do anything extra to make it even more lengthier. So just part of the process. So you just need to be prepared and be ready. Okay, don't start watching lecture videos during the test. That's not going to work. Okay. Especially problems 1 and 2 could be slightly long. Yeah, that's how it is. 3, it's not 1 and 2, actually 2 and 3. These are these. 1 should be pretty easy. 4, please read the question. Okay. Think I make it in boldface, do not solve, and still some students sit and start solving really hideous things, because I have not set up those questions to be solved. So if you start doing it, you're going to just waste time. Okay. And I feel bad for them because, it's just horrible things that come out of it. So. All right. Any questions about what you should study for the test or what you should expect? Or no surprises. Okay. I think I've done some examples like number 4 in class. So just you might want to make use of homogeneous solution while you're deciding your YP. Okay. Okay, so I'll probably ask at the end of the lecture if you have anything that you want me to go over. Okay, but let me just go forward with my chapter 3 stuff for now. Okay, so yesterday we were just starting on section 3.3 and 3.4. Okay. And tomorrow's lecture is again short, okay, half an hour maybe. So these are probably the really unusual kind of material in this course. Okay, the discontinuous input and the second shifting theorems, all that stuff. We mentioned the first shifting theorem yesterday. That is nothing unusual. So the second one is coming today later. Okay. Discontinuous input, shifting theorem, and yeah, I think that should be it. So we defined this unit step function yesterday. Okay. U of t minus a, also called the Heaviside step function because he was the one who designed it, to be equal to either 0 or 1 depending on where you want to start it. Okay, so this is for t less than a, again assuming that t is positive, less than or equal to this, and then 1 for t greater than or equal to a. So this is called the unit step function or the Heaviside step function. Okay. Again, this notation here, it's not really a multiplication. It just tells you that the input is delayed by some time a. Okay, so it shouldn't read this as u times t minus u times a. It's just a notation that it's a delay function. Okay, so the switch is off till t equal to a. Okay, that is the 0, and then at t equal to a, there is a signal of strength 1 that is kicked off. And I think some textbooks also denote this by u subscript a of t. Okay, that is just to save space because when they write this, they take up more space. Okay, but it's the same thing. It's a little blurry. Let me see. Don't have a lot of control over this, but sorry. First, I thought it's just my eyesight that is bad today, or It's strange. So it's slightly better, or people online? Sorry for the delay here.
I think it's a bit too close up right now.
Oh,
Yeah.
really? Yeah, I know that there are parts which are cut off, but are you able to at least read it better, or?
Kind of, but I thought we could read it fine before.
All right, let me see. I don't know what is different today than what I had yesterday, but can somebody here just check it and see if it is? There's only one camera, which, I mean, the controls are here. It's pretty straightforward in terms of moving it around. Is it blurry for you? Just blurry? Hmm. It's clear here, is it? And then it's not clear on that part? Yeah. I can, okay, let me try to. I don't want to pivot it too much and make it worse, so. Yeah, let me know if it gets worse, okay? Let me just try to keep it at the same, and if it is unbearable, just let me know, okay? Feel free to just unmute and let me know if it is not readable, okay? Sorry for, I'll let the IT people know about it. All right, so this is the basic definition of the unit step function or the Heaviside step function, okay? And again, the idea here is to either switch it on or off, right? So when you write, for example, f of t equal to 5 times u t minus 1 minus 8 times u t minus 5 plus 12 u t minus 9, okay. The idea here is to break it down into individual pieces as a piecewise continuous function. So this is equal to 0 for t less than 1 and equal to 1 for t greater than or equal to 1. Okay. This is equal to 0 for all times which are less than 5. Okay. And 1 for t greater than or equal to 5. And this is equal to 0 for t less than 9 and 1 for t greater than or equal to 9. That's the meaning of the step function. It's just either turning the switch on or off depending on the value of 0 or 1. Okay. So you can break this down into individual pieces. So f of t, when you start, there is none of these active, okay, because this is off, this is off, this is off. Okay. So initially, the function is equal to 0 for the time between 0 and 1. Okay. And then at t equal to 1, the first switch is on, and that input has a strength of 5. So it is equal to 5 for 1 less than or equal to t less than 5. Okay, that is where the second one is going to be active. These numbers are chosen at random, so this 5 here has nothing to do with this 5 here. Okay. Can you tell me what will be the next value? So I'll write the interval here. So 5 less than or equal to t less than 9. Okay. -3 because you have 5 minus 8. Okay, so it's -3. Good. And the next interval would be starting from 9 and ending nowhere, right? Unless you restrict your value of t greater than or equal to 9. And what is that value going to be? 5 minus 8 plus 12, which is 9. Okay. So in case you're wondering where these numbers came from, okay, this is 5 minus 8, and this is 5 minus 8 plus 12. So that is the piecewise continuous function that is represented by this notation here. Okay. And now we could make a sketch of this function. Sorry for cramming it here. So it's going to be broken out at 1, 5, and 9. So it's 1, this is 5, this is 9. So initially it starts from t equal to 0, okay, and then up to 1, it is just 0 here. Again, the hollow circle just means that you're not including that value there. Okay. At t equal to 1, the value is 5. So somewhere here. And that continues till you reach t equal to 5. Okay. But that's t less than 5, so it's a hollow circle. Nice to mark it here. And then it's -3, so which is somewhere down here. Okay. And once again, it jumps up to 9. So when I say sketch these functions, it's just a representation of what these values are at different intervals. Okay. Doesn't have to be anything sophisticated, but you should know what the notation means. Okay. Again, the application of this function is to either switch a function on or off in terms of application. So if you take a spring mass system, and if you don't want your external force to last the whole time, okay. So if you probably want to start it after 2 hours, you can keep it 0 for the first 2 hours and then start it after that. So that is why these functions are useful in applications. All right, any questions on writing a step function in terms of the discontinuous parts? Any questions? Now let's do it backwards. Okay, so write this carefully. This is important stuff. Erase this. So next, you're given f of t as, for example, f1 of t for 0 less than or equal to t less than t1, and f2 of t. Let's start with a simple case, and then we can start. The input inside the. So let me try to understand that question. So if I'm talking about this value here, the t minus a. So if this t minus a is negative, then the value is 0. And if the t minus a value is positive or equal to 0, then the value is 1. So what it, yeah, okay. So that's what the delay is just being denoted by. So if t minus a is less than 0, then the value is equal to 0. And if it is greater than or equal to 0, it's 1. Okay, just to understand from a notation point of view. Okay. Because we haven't achieved that time yet. And once you achieve the time, it's 1.
Yeah,
That's a
thank
good-
you.
Yep. That's a good way of looking at it. So the question is, how do we write this piecewise continuous function in the form of the representation given there in terms of the unit step function? Okay. In this case, there is only one point where it's breaking off. So let's start with the simplest case. Okay, 2 pieces. So it's going to be just 1 u of t minus t1. Okay. Here is my way of doing it. Okay, so you don't have to stick to this one, but I think it's convenient if you do it this way. But there are a million different ways of doing this. Okay, so one way is this, and I'll strongly suggest that you use this. You can write f of t to be f1 of t plus u of t minus t1 times f2 of t minus f1 of t. So let's try to understand what's going on here. Okay, so look at the piecewise continuous function for the first t1 seconds or first t1 whatever units of time you have. It's only equal to f1. Okay, and then the second piece, it's only equal to f2. And what we know out of the meaning for u of t minus t1 is that this is equal to 0 for t less than t1, and it's equal to 1 for t greater than or equal to t1. So either the switch is off or it's on. Okay. When the switch is off, you will still recover f1 of t. Okay. For t less than t1. Okay, because this function is equal to 0, so you have f1 of t. So there is no magic there. When it's equal to 1, it will be f1 plus f2 minus f1. Okay. So the way I've written this function, it makes sure that it cancels out any unnecessary parts. Okay, and that leaves us with f2, and that is what we have here. f2 of t for t greater than or equal to t1. Okay, that's what the switch is doing, right? It's either turning it on or off. This is useful to later represent piecewise continuous functions using Laplace transform, okay? Because ultimately we're going to make use of this Heaviside step function, so a proper representation of all piecewise functions would be useful there. So it's important that you understand how to convert that form into this form. Okay. Previously we did from u to the piecewise function, now we are going backwards. Okay. So let's write this in a more general way. So this is only with 2 pieces, but it's going to work for any number of pieces. That's a good thing. Okay. So in general, if f of t equal to f1, f2, f3, dot, 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 dot. Okay. And these could be functions of time, or these could be numbers, I don't care. Okay. This is for 0 less than or equal to t less than t1, t1 less than or equal to t less than t2, t2 less than or equal to t less than t3. So all you're doing is now just adding more and more term slightly to the right. Yes. So then I need to. Oops. Does it cover the whole thing? No. Okay, I think that covers the whole thing. Sorry about that. Okay. All right, so if in general, if you have f of t equal to f1, f2, f3, dot, 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 okay, we could just add similar terms on the right side and make it kind of appear, disappear, depending on how you cancel those terms. So this is equal to f1 plus u of t minus t1 times f2 minus f1 plus u of t minus t2 times f3 minus f2. Okay. So once the switch is turned on, it's not being turned off, right? So it's a question of when you're turning each switch on in a sequence of timely fashion. Okay. U of t minus t3 times f4 minus f3 and so on. Typically, you won't deal with more than 2 or 3 pieces, but you could just keep on writing this for any number of terms. So let's write a couple of examples. Example 1, f of t equal to 0 for t between 0 and 2, equal to 5 between 2 and 8, and then 12 between 8 and infinity. Yeah. Still a little confused about why it's blurry there, distracting me, but okay. So it's useful to give some names to this. So this is your F1, this is your F2, and this is your F3. Okay. And these are your T1 and T2. So you're trying to write this using the Heaviside step function. Okay, this is a piecewise function, and we would just prefer writing it as one term or one function instead of bits and pieces. Okay. So it's going to be F1, which is 0, plus F2 minus F1, which is, so it's going to be u of t minus t1, which is u of t minus 2 times 5 minus 0. Okay. Plus u of t minus 8 times f3 minus f2, which is 12 minus 5. You don't have to write 5 minus 0 and so on, but just to make it clear that I'm just subtracting the second to the first. Okay. And that's equal to 5 ut minus 2 plus 7 ut minus 8. So if you now work it backwards, initially there is nothing, and then there is 5 as the second piece, and then you have 5 plus 7, 12 as the third piece. Okay, so it works both forwards and backwards the same way. This is very important. Okay, please write it carefully, keep it nicely marked and boxed. So can you do the next 2 examples yourself and see if you are comfortable with this process? So t equal to -9 for t between 0 and 3, and t square minus 6t for t greater than or equal to 3. Let's do that first and then do another one later. So my question is to write this using u of t minus 3. Okay. Okay, so once again, let's label this as F1 and this is F2. And luckily, we only have one time that we need to worry about here, that is T1 equal to 3. Okay. So this is going to be F1 plus U of T minus 3 times F2 minus F1. And that's going to be equal to -9 plus U of T minus 3 times F2 minus F1, so it's going to be plus 9. Okay, so T square minus 6T plus 9, which you will see later that it's very useful if you just write it as T minus 3 whole square. So we'll save that example for later. Okay, that's a pretty neat example to show some nice things that we're going to do with these weird functions. All right, so just keep those things in mind. We'll come back to these when we start applying these problems later for some spring mass applications. Okay. Don't forget about this notation of going back and forth between piecewise function and the U function. Okay. Very important. All right, any questions on what this Heaviside step function means or how to go back and forth? Any questions up to there? Online, any questions? All right, now let's see what the Laplace transform for each of these things would be. Okay. So next. What is the Laplace transform of U of T minus A? Okay. Again, we are only concerned about time being on the positive axis. Once again, if you don't know something, start from definition. That's going to be 0 to infinity e to the power of negative s t times U of T minus A dt. We still maintain the same definition for this function. This is equal to 0 for t less than a, 1 for t greater than or equal to a. So the reason I'm doing that is because we can now break this integral from 0 to infinity at this point a. Okay. So it's integral from 0 to a e to the power of negative st times U of T minus a dt plus a to infinity e to the power of negative st times U of T minus a dt. Because the interval from 0 to infinity is a continuous interval. Okay, you can break it anywhere you want. It's a basic property of definite integrals that if you take any interval between 2 points, okay, you can always break it into finite definite integrals and write it out. From 0 to a, this function is equal to 0. And from a to infinity, it's equal to 1. So suddenly a derivation that would have probably looked very complicated becomes very easy to do. Okay. That first term is shut off, the second term is 1. So it just becomes the integral from a to infinity e to the power of negative st dt. Which, admitting that I'm going to be a little bit sloppy with the improper integral part here, okay, it's going to be just 1 over negative s times e to the power of negative st from a to infinity. E to the power of negative infinity is 0, so it's 1 over negative s, and that's a limiting case. Okay. The limit as t goes to infinity of e to the power of negative st approaches 0. That's what the correct way of saying this is. Okay. So it's going to be 0 minus e to the power of negative a s. Okay, remember that t is a variable, a goes in there. So if you just clean it up, you get negative of this times negative of this. That's going to be a positive term. Okay, e to the power of negative s over s. So we have the result now, which is also in your table. Okay. So I think this is case number forgot 12 or 11. Laplace transform of u of t minus a is e to the power of negative a s over s. Okay. Super important because that is how we are going to introduce this thing into our differential equations. Okay, so we need this result to make use of later. The good thing is it's a pretty easy looking function here. Okay, there is nothing complicated about the Laplace transform for e to the power of u of t minus a. So that is important. So a lot of important things today. Okay. So the next one is super important. So this is important. Next thing is very, very important. Your success in chapter 3 is kind of going to be based on this particular fact. Okay, it's called the second shifting theorem. So let me just write it down, derive it, and then I'll tell you what exactly this means and why is it useful. So if the Laplace transform of f of t is capital F of s, okay, that's something that we are familiar with. So for an ordinary function, you have a Laplace transform. Then the Laplace transform of u of t minus a times f of t minus a. What you're doing is you're taking the function and kind of delaying it before you apply it. Okay, so it's called a delayed function or delayed input. So you're not applying this function right away. You're waiting till you reach t equal to a, and that is what is going on here. Okay, but the delay should be applied to the function as well. And this is equal to e to the power of negative s times capital F of s. It's a tricky theorem, okay, because if you're not careful, you might think it's just a product of the individual Laplace transforms. It's not. Okay, so this is not, and this is not a typo. I'll show you why it is not what you think it is. Okay, so it's not equal to e to the power of negative s over s times f of s. That's what you would expect because you know the Laplace transform of u of t minus a is that one. Okay, Laplace of this is this. So why not just multiply those two? Okay, that's not right. It is e to the power of negative s times f of s. There is no denominator here. So be careful about this theorem. It's dangerous stuff. Okay. You end up doing a whole lot of unnecessary things if you're not doing this properly. So let me just quickly show you why this is the case. So proof. That's going to be the integral from 0 to infinity e to the power of negative st times your function, which is u of t minus a times f of t minus a dt, because that's what you're trying to do here. Anytime I don't know something, I go back to my definition. All right, once again, just break it up into two parts, okay? Because the step function is just assigning a value of 0 or 1 depending on where you are. So this is the integral from 0 to a e to the power of negative st times u of t minus a f of t minus a dt plus the integral from a to infinity e to the power of negative st times u of t minus a f of t minus a dt. So I'm just making use of what the step function means. It's either 0 or 1. Okay. This thing is 0 and this thing is 1. So what we have is the integral from a to infinity of e to the power of negative st times f of t minus a dt. Almost there. Okay. The only problem with this thing is the lower limit is a, and we have a shift here by t minus a. We need to kind of control that part. Okay. And once you do that, we are in business. So let's plug in t minus a equal to v. I cannot use u because u stands for the step function, so it's a v substitution here. Okay. So dt is dv. So it's a very harmless substitution, right? This becomes v, this becomes dv. Now what about the limits? When t is equal to a, the lower limit v becomes a minus a, which is 0. That is what you wanted to get, right? The Laplace transform always starts from 0, not from some arbitrary number. So doing this simple shift of variables, achieve the lower limit is equal to 0. Okay. The upper limit is still infinity, and when t approaches infinity, v approaches infinity. Adding or subtracting something from infinity is not going to change anything. So overall, something that looked pretty crazy to start with, okay, just comes down to the following. It's the integral from 0 to infinity e to the power of negative st times f of v dv. Yeah. The time. Oh, this one. Yes, yes. I should. So this is t equal to a plus b. Thanks for reminding me that. F of v dv. Okay, that would have looked awkward without it. Oops. Negative s times a plus b, which you can write as e to the power of negative as times e to the power of negative vs, okay, using law of exponents. And you can take this outside the integral because the integral is in terms of v. Okay, so it's going to be e to the power of negative as times integral from 0 to infinity e to the power of negative v s times f of v dv. Now this here is nothing but the Laplace transform of f of v, okay, which you can call as capital F of s. Whether you call this as v or t doesn't matter because this is a dummy variable. Okay. What the name you give to this variable is irrelevant because overall this integral is just done with respect to the same variable here. Okay. So you can just call this as t if you want. And that recovers the Laplace transform for f of t, which is capital F of s, as I wrote there. So this is equal to e to the power of negative as times capital F of s. So you can see why this theorem does not have a denominator of s, okay, as you might expect. Okay. It's very easy to get lost here. Okay. So it's not really what you see up there. It is the product of e to the power of negative s times Laplace of f of t. Okay. Please copy this correctly, okay, because it's going to be very useful in doing all the problems in 3.3 and 3.4. Okay. All right, so let me just mention a couple of important things about the second shifting theorem. Okay. Notes. To apply the second shifting theorem, one requirement, which is an important requirement, is that both these terms should be shifted by the same number a. Okay. If not, you have to make something happen there. It's very important that both those things are t minus a for the same value of a. Okay. The left-hand side must look like u of t minus a times f of t minus a. Because that is how it was derived in the first place, so we have to preserve that one. Okay. So the question is, what if it is not? Okay. So if it looks like this, u of t minus a times f of t, you need to go in there and do some manipulations. Okay. So you have to do something like u of t minus a times f of t minus a plus a, so that you kind of do and undo something and bring in this necessary f of t minus a into the picture. Okay. This is a very useful thing to do in problems where it has u of t minus a, but it does not have a corresponding f of t minus a. Okay. And when is this applied? The second shifting theorem is necessary when the input is delayed by a certain time t equal to a. You can take a spring mass dashpot example if you want. So in chapter 2, we assume that there was an external force coming in, f of t. Chapter 2, this just started from t equal to 0, and there was no restriction on how long it was there. Okay. You couldn't do anything because it was just a continuous function. Now we have got more capabilities. We could shut it on, shut it off. Okay. So here we want to delay it by say t equal to 5 hours or 10 hours or 1 day if you want. Okay. Then all you have to do is apply the step function correspondingly, and that will give you a delayed function input. You couldn't do this in chapter 2 based on what we did, because there the assumption was that the function was continuous everywhere. Okay. Now we can break it up and look at places where it's actually active and places where it's inactive, we can shut it off. Okay. So that is the application of the second shifting theorem. And to make that happen, sometimes it requires some manipulations. It can get a little bit tricky at times. On the third note, as I wrote earlier, this is not at the expense of repeating myself. Okay. L of u t minus a, f of t minus a is not equal to this. Which is probably about you might think it is, but it's not. So even if it's a negative statement, you still probably need to write it so that you don't get into trouble. Okay, so now let's try to slowly get used to this. Okay. Any questions about the second shifting theorem? So this is case number something in your table, case 12 or case 13. 13. So everything is in your table. You just need to copy it down correctly. Okay. You don't have to memorize anything. You don't have to derive anything. Everything is done for you. So all you have to do is look at the table and carefully copy it down. Before I erase any of these, do you have any questions? All right, so let's do some examples. Let's start with easy ones and then we will kind of make it complicated. Let's go back to that example we did earlier. Okay, find the Laplace transform of the piecewise function f of t equal to -9 for 0 less than or equal to t less than 3 and t square, was it -6t or +6t? Sorry, t square -6t for t greater than or equal to 3. So this is a problem that is kind of designed to work nicely in this situation. Okay. And we already did this. I think 2 or 3 examples ago, we did this as f of t equal to -9 plus e of t minus 3 times t minus 3 whole square. And this is what I mean by saying that these two terms should look the same all the time. So if that was not t minus 3 whole square, then it becomes a problem. So now we can take the Laplace transform of that function, term by term, which is the Laplace of -9 plus u of t minus 3 times t minus 3 whole square. Which can be written as the Laplace of -9. Okay, so there's nothing fancy here, plus the Laplace of this product, okay, L of u t minus 3 times t minus 3 whole square. So this is case number 1, and this is case number 11, okay, the second shifting theorem. So this is your A, okay. So it's u of t minus A, and this is your f of t minus A. So some basic understanding of function is useful here. So f of t minus 3 is t minus 3 whole square. Okay, that is a delayed function. Right? Let me ask you a pre-calculus question. Then what is f of t? If f of t minus 3, which was kind of delayed, was t minus 3 whole square, what should have been the function that was already there? T square. Okay, you should be able to look this back and forth. Okay, this is the function that gave you this. Now you're going back to this. Okay. Why do you need this? Because this is what is helpful in finding the Laplace transform. Okay. Capital F of S is the Laplace transform of f of t. Which I think is case number 2 or something, okay, with n equal to 2. And that's going to be equal to 2 factorial over s to the power of n plus 1, which is 3. Okay, so what I'm doing is taking my delayed function, recover the original function, the undelayed function, take its Laplace transform. Okay. And then we can write this. So this is just your first, or the case number one, which is just -9 over s. Okay, that's the first item in your Laplace table. And then you have, remember the second shifting theorem tells you e to the power of negative as, a is equal to 3 here. So it's going to be e to the power of negative 3s times f of s, which is 2 over s to the 3. And that's where you have to be careful. It's not e to the power of negative 3s over s. Okay, this is your e to the power of negative as times f of s. You should go over this example again when you practice this section, okay, because there are not many examples in the textbook and some of them are too easy. So even if these numbers are not really all that precious, it's about what you did with this function here that is very important. Okay, so make sure that you spend time with this when you study for next week's test. Any questions on that one? All right, so let's do a few more. Okay. I want you to try the next one yourself. Find the Laplace transform of f of t equal to u of t minus 2 times e to the power of t minus 2. Okay, so it's a perfectly well set example. So that's what we're trying to do here. The Laplace transform of u of t minus 2 e to the power of t minus 2. This is a nicely set up function. There is no need to do any extra manipulations here. Okay, because this is your u of t minus a and this is your f of t minus a. So this is sorry to use the same f of t on both sides. Could have used something else here. My question to you is, what is f of t? Yep, e to the t. Okay, that is a function that got delayed by 2. So the original function was e to the t. And you can find its Laplace transform from your table, case number 3, which is 1 over s minus 1. Okay, so It's a small process there, which with practice, you don't have to go through so many steps. Okay. So this is going to be e to the power of negative 2s times 1 over s minus 1. Any questions on that one? All right, here is another one. Okay, slightly tricky. So f of t equal to 0 for t less than 4 and e to the power of 2t for t greater than or equal to 4. So there are two questions here. One, write f of t using step function. It's kind of a hint for the second part. In part 2, find the Laplace transform of f of t. All right, can you try that? So back to our previous notations, we can label those two pieces as f1 and f2, which I forgot to do there. Okay. So f1 is 0 and f2 is e to the power of 2t. So this is so that is the answer to part 1 of the question. Okay. All right. Now, so this is part 1. We need to find the Laplace transform of u of t minus 4 times e to the power of 2t. Now, there is an example or homework which is similar to this. I don't want you to panic when you see the answer to that question. It looks a little weird. The problem here is that you have a t minus 4 here, but not here. Okay. We want both these terms to look the same if you want to apply the second shifting theorem. Okay. So we need a t minus 4 here. So you just need to kind of take a step backwards, think about what you're doing. Okay. So you're going to put a t minus 4 into that expression there in the exponent. That's going to be L u t minus 4 e to the power of 2 times t minus 4, but you all know that you cannot just do something like this. Okay. You have to add a 4 immediately. Now, let's do this carefully. Okay, so this is L of ut minus 4. This is the part we need. Okay, e to the power of 2 times t minus 4. That is the religious part of it. You have to maintain that particular pattern in both the terms. And there is an extra e to the power of 2 times 4, 8, which is kind of standing out there. And let's keep it. Okay. Don't throw anything away. Okay. E to the 8 because you had a 2 outside, so 2 times 4. E to the power of 8 is some number. Okay, I don't care what that is. Just keep it. So it's e to the power of 8 times the Laplace transform of u t minus 4 e to the power of 2 times t minus 4. And again, once again, I'm not interested in knowing what e to the power of 8 is. Just leave it like that. Okay, you don't have to use a calculator or anything. Now this is in its perfect form. Okay, u of t minus a, f of t minus a. The delayed function is f of t minus 4, which is e to the power of 2 times t minus 4. Okay. Now, can somebody online tell me what f of t would be? What was the original function f of t that was delayed by 4 later? It looks a bit blurry there, but I hope you can see it just enough to know what
power
is
of 2t.
good. E to the power of 2t. Okay. And then its Laplace transform is given by case number 3, 1 over s minus 2. Okay, so now we can do the second shifting theorem, and that's going to be e to the power of 8 times e to the power of negative 4s. Okay. That's your negative as times f of s, which is 1 over s minus 2. It's not necessary to combine these two exponents here, but I think in some solutions people do it and confuse students. Okay, so if you see the answer to a similar homework question like this, or some numbers there, okay, it's just a play of the law of exponents. And this is what I meant earlier by saying that if the left-hand side is not in its perfect form, you have to do some manipulations, okay, and that is what it is. Questions? Let's do an example where this is easier than some of the cases that we have done. Okay, so example 4. Let f of t equal to 0 for t less than 2 pi. Okay. And it's equal to cosine of 2t for t greater than or equal to 2 pi. So you can think about it as a spring mass example where there's a periodic function or a periodic external force applied after 2 pi seconds. Okay. Again, find the or write using step function and find the Laplace transform of f of t. Okay, so let me get started with part one. Okay, that's going to be 0, my f1 plus f2 minus f1 is cosine 2t, and u of t minus t1 would be 2 pi times cosine of 2t. So that works similar to what we had in the previous example. Okay. Now, you may remember from high school that both sine and cosine has a very nice property of being periodic with every 2 pi radians. Okay. So cosine starts here and it comes back here after 2 pi. And that is true for every cosine 2t, cosine 3t. Okay. The graph just periodically repeats after every 2 pi radians. And the same thing with sine. It just starts from 0 and comes back to 0 after 2 pi. So it's a universal property of sine and cosine that both sine of kt and cosine of kt are periodic with a period equal to 2 pi. 2 pi radians. Okay. Now that's a big deal here because we can make a change without any further manipulations. Okay. You can easily write this as u of t minus 2 pi times cosine of 2 times t minus 2 pi. Okay. That's a free thing you could do here, unlike the exponential function where you have to compensate it for multiplying by e to the power of 8 or whatever there, right? You don't have to add a 2 pi here because of this property of sine and cosine. Okay. So don't misuse it, but wherever you see cosine and sine, feel free to apply periodicity as needed. Okay. Some questions I give a hint because sometimes students forget about this and they think they have to add a 2 pi here and make a mess out of it. Okay. So that's a free change. All right, so now we have a perfect form for applying the second shifting theorem. Okay. So L of u t minus 2 pi cosine of 2 t minus 2 pi. Okay. Once again, the only requirement is that these two terms should look alike. Okay, with a equal to 2 pi, we are in business. So now apply the second shifting theorem, and that's going to be e to the power of negative 2 pi s, right? Because it's going to be e to the power of negative s, and a is 2 pi. Okay. F of t minus 2 pi is the sine of 2 t minus 2 pi. That is my delayed function. Okay. So what is f of t? There you go, the sine of 2t. Okay. So it kind of keeps on repeating. Once you see a few examples, it becomes kind of very natural to keep doing this process for different functions. Okay. And its Laplace transform is case number something s over s square plus 4. Like case 5 or 6. Okay, so those are the typical functions you would see when you do the questions in chapter 3 in this course. Okay, but if you are using it in other classes, you will probably see more fancier functions there. Okay. All right, I hope all of you are comfortable with this now, going from left to right of the second shifting theorem. Okay. But then when you solve your differential equations, you should also be able to go from right to left, which means that you should be able to kind of just backtrack your process and retrieve your original function. Okay. So the inverse of the second shifting theorem. If you understand these things, solving the differential equations will be just pretty routine. Okay, once you understand this small annoying parts of the shifting theorem, you're in good shape. So the Laplace inverse of e to the power of negative as times f of s will be u of t minus a, f of t minus a. So I'm just writing it backwards now. Earlier I went from here to there. Now I'm going from there to here. Two things to keep in mind. Your E is becoming U. Okay. That's the easiest way to look at it. Right? All that happened was that when it went from here to there, the U became E. Now you're just going back, E becomes U. The more tricky thing here is that your f of s becomes f of t minus a. So you have to go through a small process here. F of s becomes f of t, and then you have to delay it by t minus a. So all your answers are going to look a little bit lengthy now, because instead of writing t, you're going to write t minus something. Okay. So instead of writing e to the power of 5t, you write e to the power of 5t minus 6 or something. Okay. So don't forget this part. So when you start solving differential equations, you would still do the same process, but at the end, when you're applying the second shifting theorem, okay, the E becomes U, and all the functions should be shifted by A corresponding to the value of A. All right, so let's do some examples. Find the Laplace inverse of e to the power of negative 2 pi s times s over s square plus 4. Don't know, that looks familiar. Okay. Just to illustrate how this works forward and backward, okay, I'm just taking the same function I had earlier and trying to put it backwards. Okay. So you're trying to find the f of t that would have given you this function later, right? So f of t by the inverse of the second shifting theorem, okay, the E becomes U. Okay. That E term is not playing any other role here. Okay. In all the problems, the E becomes U. And this part, f of s is s over s square plus 4. Its inverse function, if you look at your table, would be cosine of 2t. Okay. Then you shift it by the same number here. So f of t minus 2 pi will be cosine of 2 times t minus 2 pi. But in this case, though, you don't have to do that because cosine is periodic. Okay. So even if you don't do this in this particular problem, you're safe. That's because of the periodic property I wrote somewhere. Yep, right there. So f of t minus 2 pi, it's still cosine of 2t, and you're back to where you started. Okay, so can you do the next few? Example 2, find the Laplace inverse of e to the power of negative 5 s times 1 over s plus 3. Can somebody tell me the answer? Just slowly. Can somebody online want to try?
Is it
Mhm.
is it u of t minus 5
Okay, good.
times e to the negative 3t?
Negative 3. Almost there. Negative 3.
Oh, the times t minus a.
Yeah. T minus
T minus-
5. Okay.
Yeah.
So again, this is f of s equal to 1 over s plus 3. Where f of t is e to the power of negative 3t. And since the value of a, the delay value is 5, f of t minus 5 is e to the power of negative 3 t minus 5. So at the end of it, it should look exactly the same as this part here. The only exception being any function which is periodic, okay, that is because it's kind of built in there, but otherwise all your answers for the second shifting theorem should have these two terms looking the same. All of you understand this process? All right, so now we can go back and start doing our differential equations. Okay. So keeping in mind all these new concepts, now we can go back to initial value problems involving step functions and delayed inputs. Good news, okay, 95% of it's the same thing. So whatever you did yesterday for ordinary cases, you just keep doing the same process. So for example, if your equation looked like this, a y double prime plus b y prime plus cy equal to u of t minus t1 times f of t minus t1. I'm just writing a generic case. It may or may not look like this all the time. So this function is not active till you reach t equal to t1. Okay. That's the meaning, right? So take the Laplace transform on both sides. Okay. You should be able to do it based on the tables that you have. Apply the initial values. Okay. 2. Solve for y of s algebraically. And when you take the Laplace transform of both sides, for this term, you're actually applying the second shifting theorem. Okay. Just keep that in mind. So you should look at the function carefully and do what is required. Okay. So if that is the kind of function you have to apply a second shifting theorem on the right hand side. Solve for y of s algebraically, and then find the inverse Laplace transform. Here is where anything that is different is going to happen. Okay. Apply the second shifting theorem backwards. That's what we were doing in that example. Okay. And in particular, the only thing that you should not forget to do here is to shift all your functions by the corresponding value of a. Okay. So do the necessary shifting. Because if there was any input that was delayed, its output also should be delayed accordingly. You cannot have the output starting from some time it was not there, right? So for example, if your function was applied for t greater than 10, okay, the output should be shifted by the corresponding number, otherwise you're going to get the wrong answer there. Okay? All right, so I'll do a small example today, just to show you what the small expectations are, and then we'll do some bigger examples tomorrow and on Tuesday. So it's going to take a couple of lectures to get done with these two sections. All right, so let's do a first order equation just to show how this works. Example, solve y prime plus y equal to u of t minus 2 with y of 0 equal to 0. So I just want to show you how this works. That's it. So it's a system where you are applying a force of magnitude 1 at t equal to 2 and keeping it alive for the rest of the time. Okay. All right, so it's a first order equation, so there is no y double prime or y prime of 0. Okay, so L of y prime plus L of y equal to L of u t minus 2 . This is case number 11. Okay. So just L of u of t minus a, which is case number 11. This is s times y of s, and this is just y of s. So very humble start to this set of problems. But it has got enough things to keep you busy. Okay, we have s plus 1 times y of s here, equal to, if you look at case number 11, not 12, this is e to the power of negative 2s over s. That is the Laplace transform for the step function itself, not the second shifting theorem. So y of s equal to e to the power of negative 2s times the remaining part is 1 over s times s plus 1. So that's the part I wrote as step number 2, the solve for y of s. Now you know, hopefully, that you need to apply partial fraction here. Okay. When you do that, try to keep this term outside, because this is not going to help you in any way do this partial fraction in this term. Okay. Just keep it outside. All we need to do with this later is to bring the u back to the solution. Okay. This is a humble suggestion. Please don't mix it up and try to complicate things. Okay. So partial fraction for 1 over s times s plus 1 equal to a over s plus b over s plus 1. It's not very difficult to do this. It's 1 equal to a times s plus 1 plus b times s. So if you set s equal to 0, we get a equal to 1 and s equal to negative 1 gives you b equal to negative 1. So it's one of the easiest partial fractions you could do, 1 negative 1. One over s minus 1 over s plus 1. Now invert it. Okay, this is where the second shifting theorem comes in. So the step 3 written there, y of t. Make some room here. So y of s equal to e to the power of negative 2s times 1 over s minus 1 over s plus 1. Okay. The only new thing here is that when you invert it, you need to do the second shifting theorem properly. This will give you u of t minus 2. Laplace inverse of 1 over s is just 1. Okay, there is no t in there. Okay, that's just a constant 1. So there is nothing to shift there because it's a constant. Okay, you should need a variable t to do any shifting. Okay. And this would be minus e to the power of negative t, but it's going to be shifted by this 2. So if you want to write a couple of steps there, the f of s is 1 over s plus 1. Its Laplace inverse till yesterday would have been just e to the power of negative t. Okay. But now we are also doing the shifting backwards. So f of t minus 2 is e to the power of negative t minus 2. So it's not a permanent change of the function, it's just delayed by that much time. Okay. So you just need to absorb the delay property into your solution so that nothing is starting till you reach t equal to 2. So whatever problems you do in section 3.3 and 3.4 is the same mechanics. Okay, so if you understand this concept, you are in good shape. But you might take some time to get used to this shifting process. All right, so we'll do more examples tomorrow, okay, and on Tuesday. So in the meantime, I just want to ask you, do you want me to go over anything for tomorrow's test? Any examples you want to see, or all of you are in good shape? So suppose I ask you some questions, will you be able to tell me the answers right away? So let's see. So for tomorrow's test, some sample questions. Okay. Suppose you have y double prime plus 9y equal to sine of 4x plus x square. Can you write the yp for this? Do not solve it. Okay. So just to show you what I mean by saying write yp, do not solve. So for your convenience, I just wrote the homogeneous solution there. So in case you need that. And this is my answer. Tell me if that is right or wrong.
Plus dx plus e.
Plus bx plus e. Okay, that is good. So that takes care of this term, right? Not that I'm giving different letters for each of these. Okay, don't repeat A and B here, and just as a matter of keeping it distinct. Okay. So is that part clear to everyone? All right. Multiply by x in the.
Oh, no, sorry. Plus I know. That's wrong.
All right. So the answer is no multiplying x, right? This is okay. All of you agree that this is okay? Online? Any? Yes, I hope the wrong is for the second part, not for the first part. Now let's tweak it because we said something, and let's see if this is applicable there. Okay. I'm not writing the x square part. I think all of you got that part. And the same homogeneous solution, so you can focus on the YP now. No, 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 no. Please don't solve for anything. Okay, that's the whole point. These problems are worth probably 2 or 3 points. Please don't. Okay. So it'll clearly say do not solve, and I hope it's clear. Okay. You're not going to finish the test if you're going to solve for all these things. Look at the number of points and budget. It's worth 2 or 3 points. So it's a sample of what or where you should stop for these questions. So write that YP and move on with your life. Okay. It's a long weekend. Don't make it worse. All right. What about that one? Let me ask somebody online if you could tell me the YP for example 2. Just think it'll be easier if you just unmute and say it, or
ax cosine 3x plus bx sine 3x.
okay, x cosine 3x, and what is the next one? I forgot.
Plus bx
Okay,
cosine
good.
3x.
B plus bx sine 3x. As long as each term here is linearly independent with your YH, you're safe, right? All of you agree with this? What if you had this one? Y double prime plus 9y equal to x square cosine 3x. You need a lot of letters in the English alphabet to do this. Okay. All right, who wants to try it? Maybe someone here could start. let me write the typical YP, okay, so that it's this is what I usually do. Just write it as though nothing is wrong, and then you can start fixing it. Okay. It's a polynomial of degree 2, so that must be a polynomial of degree 2 here. Cosine 3x, and please don't use the same letters here. Dx square plus ex plus f. It looks bad, right? It's a good hint that you won't be able to, or you won't be asked to solve this fully. Okay. Okay, is that right? What is wrong here? Is there anything that is linearly dependent with the homogeneous solution? Yes, it's difficult to spot it, but it's right here. Okay. So you need to kind of keep your focus on those terms. So how do you fix this now? Multiply by x throughout. Okay. So the correct one would be ax to the 3 plus bx square plus cx, no plus d, okay, just plus cx cosine 3x plus dx to the 3 plus e x square plus fx sine 3x. So you should do this only for those terms which are linearly dependent, but when you do it, make sure that there is nothing else which is linearly dependent within itself. Okay. You cannot just multiply this alone by x, that will leave you with these two the same. So have a good idea about what you're writing term by term, and take your time to just verify it. Okay. And I know you have nothing better to do during the long weekend, so this is something you could do later, right? Memorial Day, wake up in the morning, start doing this. It's a good exercise. All right, so I'll stop there. Okay. I have office hours today from 12:10 to 1:10. So if you have any questions about this or other things that affect your life, you can come back and talk to me there. Otherwise, I'll see you tomorrow for a short lecture and then test 2 tomorrow. Okay. What's wrong with the bx square term? The bx square is okay, right? This is linearly independent with my YH. That's all we care about. Is that what you're asking? Okay, yeah. Just write out all the terms. Make sure that no two of them or none of the terms in your YP matches with YH, as in they are not linearly dependent. That's all we are caring about here. Okay. Hope that is clear.
Thank you.
Can stop recording and then